Hello. Okay, so we are live after a long break after Holi and all. So today we'll be solving two problems. Okay, so we'll be solving two problems from cses only, and yeah. Okay, so let's start with teleporters path. Okay, and levels m teleporters between them. You win the game if you move from level 1 to n using every teleporter exactly once. So basically, if you use the edges only once and can go from 1 to n, that is what it is asking. So we'll start from 1. We will traverse every edge. Okay, we will keep track of the visited edge, and if in the process we encounter the nth level, we will be saying that it is possible to do it, and we'll print the path for that. Okay, so we can do a DFS in this. We can do a DFS. Teleporters path. We'll take this in as input. Okay, paste it, zoom it out, sorry, zoom in or enlarge it, whatever. Put this here and we'll draw the graph. So 1 is connected to 2. It is a directed graph. Okay, 1 can also go to 3, 2 can go to 3, and 3 can go to so this is the path. So our task is to go from 1 to 5 using every edges, right? Using every teleporter exactly once. So using every teleporter exactly once. We'll start from 1. Okay. Before that we need to check some things, like if the given graph is connected or not. Okay, and if see, for a directed graph to be to have a Euler path, okay, there are some things that we need to check. For example, whether there is Of course, first is a connection check. Second is basically that there is exactly two nodes for which the in and out degree is not equal. Okay, and for every other it needs to be equal. And other than that, I think these two are the basics requirement for that. Let me check. So Euler path for directed graph. And we also need the path to start from 1 only. So if we see that the for node 1 the out degree minus in degree is not equal to 1, then we will not be able to start from this node. So there is no rush to traverse every teleporter. Okay, so we will check that. So we will check that. First we need to calculate the out degree and in degree for each node. We also need to check the connection. And then normal DFS. Okay, so let's try to diagram this. So here if we make that out and in degree graph, the table for 1 out degree is 2, in degree is 1. For 2 out degree is 1, 2 and 2. For 3 it is 1 and 1. For 4 it is also 1 and 1, and for 5 it is 1 only. So you can see that this will be our starting node and this will be our ending node. Okay, we will start from 1. 1 is in the stack currently, or is it in the stack? Okay, 1 is in the stack currently. Let me simulate this also. So our stack is here. So 1 is here. Then we will see whatever outgoing edges it has. So we have 2 and 3. So we will put 3 here. Okay. And from 3, so we have 3 and 2. So we will put 2 and 3 here. Okay. From 3 we can go to 1 again. Okay, we can go to 1 again. Okay, so whatever node that does not have any, so does not have any remaining edges, right, that will be marked as fully processed, or that will be, and that we can include that in our list path basically. So if we start from here, so we will put 2 and 3 in the stack. We'll pop 3 out of this. Okay, we'll pop 3 out of this. Okay, we popped 3 out of this. And 3 is only edges to 1, so 1 will be put here. Okay. Now from 1 we see that the edges have been removed, right? 2 and 3 have been removed and put it into stack, right? So 1 we will remove it, and this will be in our path then. Okay, we come to the other see so we start from 1. 1 is at the top right now, and its edges are not empty because this is like this: 1 2 3 and 2 4 5 3 1 4 2 and 5 none. Okay, so we put this in the our stack. Okay, and then we will remove it. We have maintained a set for which edge have already been visited or not, checking which has already been visited or not. So from here we can see that this 3 has not been visited, so we will push 3 here and also put this here. Okay, okay. No, it is a directed graph, so I will only put 1 3 here. Now we have another node, but we will not do it. We will do it. We did this is a DFS, right? So we will go back with stack. We will traverse only using stack. So 3 is here now, and for 3 there is only one connection here, so we will put here, we will pop it from here. Okay, this is it. Now now that we have deleted 3's edge and put it into the stack, we will again not pop out, we will again pick the top element of the stack, which is 1 right now, and whatever is the last element in the edge list, we will put it into the stack and pop it from here. Okay, we will also put 3 1 as visited, and here 1 2 as visited as well. So 1 2 is also visited. Now from 2 again we will pick it from 2. There are 4 and 5. There are 2 connections outgoing. So suppose I put 5 in the stack. Okay, I put 5 in the stack, and then from 5 there is nothing, there is nowhere we can go. Okay, when we peek again from 5 there is nowhere we can go, so the only thing is that we remove it from the stack and add it into our path. Okay, we add it into our path. Then the next, again we will peek in the stack, there is 2, and we will put 4 here. Then we will peek again and we'll put 2 here and remove it from here. 2 is also okay, so 2 has not okay. So we can see that 2 is empty now, so we will add this also in the path. So remove 2 and then 4 also will be removed in the similar way. 2 is already been removed, so no, when we are traveling back, backtracking, we will put 2 again here. Okay, now for 1 also is instead, and 3, then this is actually the order. So if we reverse it, so we will have 1 3 1 2 4 2 5 and just like this, 1 3 1 2 4 2 5. So yeah, we will do this. We will do this, and for that I think we can just copy and paste this code. We'll copy paste this code and do some minor changes. Okay, not this. We'll check if out degree of I minus in degree of I is double equal to 1. So we have 2 conditions, basically checking if it is a valid Euler path or not. Okay. If start is not equal to 1, okay, this. We don't need this. We don't need this. And yeah. 131245. Yes, it works. Let's just submit it. Let's see. Okay, some wrong answers here and there. I think there is one check that I'm not doing. This count is basically keeping track of all the other you know nodes which has this type of configuration where the difference is exactly c's this one connected component one. Okay, so I think I did I checked everything. I think no, this connection no. Okay. Okay, so this check is basically for any node which is which is a stray node but does not have any edges. So we could include that in our Euler path or cycle, but in this question it is specifically asked that we need to go to an nth nth node. So let's see if there is a possibility that this ith node which is not visited is n. Okay, then of course it will be impossible to reach from one. Why am I checking this? Using every teleporter exactly once. So the length of the path will be the total number of edges plus 1 only. Okay, so m plus 1. If it is not m plus 1, then it is an issue. Okay, if it is not m plus 1, then it is an issue. I think that alone can handle most of the edge cases, but still This should take care of everything now. Let's try to submit it. That took care of everything. Okay, Hamiltonian flights. I'm not sure how Hamiltonian. What is the question? Possible Hamiltonian paths. Total number of Hamiltonian paths. Okay. I want to go from 1 to n, ensuring that I don't travel any node twice. So there should be a connectivity. First we can check that connection check, then then what? This is a max flow question, right? I've never solved a max flow question actually. Max flow in graph. Oh. It's a DP question. Oh. De Bruin sequence. I need to study De Bruijn sequence. Is there any simple question that I can solve today? Because I want to solve only two questions. Let's solve string question maybe. Okay, I don't like string questions. I'm going for greedy. Distinct values in the list. Distinct values in the list. Set. Simple set will work. Yes, a simple set will work. So let's see how many greedy problems I can solve. So in graph I need to study maximum and minimum flow. There's also Hamiltonian path and Euler path as well. There's also minimum edges to be removed so that the graph is a disconnected graph. That is also a concept I need to learn. Okay. So there are some catch up for me to do in graph theory. So I will do that. Why is it wrong? What did I submit? Map. Okay. Okay. So we need NMK. Okay. And we have the apartment size. So just call it A, and we'll take the input Okay, we will take the input. Size of each apartment. Done. Now we will sort the you know what, we will put this in a map only. Okay, okay. Basically our customer's demand is this, and we will see if we can find anything close to so auto upper is basically we need only check for lower bound and upper bound only. Think lower bound will work. Okay, so our first priority is to give them the okay, I'll sort it first, then it will be easier. So I'll sort this, and after sorting it will become something like it will become this 45 60 60 80. Okay, and over this is like this. So for 45 we can check for the lower bound, which will be 60 only, and the difference between them is 15, which is not acceptable, so we will move ahead. We will check also if this is acceptable, but if it is not, then we will move ahead with 60. We see that this is done, so we will increment the count. For this it is not, so we will move that. For this it will be end of the okay. C minus K. So, will it work? Let's try. I'm not sure if it will work. Really. Keys 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the power 9. Okay, if not this, then I have a two-pointer approach. So I'll move with this. Okay, and I need to do it for all the okay. So I'll check if AI. So I'll need one more. If AI Let's try this. This two-pointer approach. Okay. Sorting, searching. Oh, this one I think I can do. This one I can do. Maybe not. This is basically overlapping intervals in greedy. Overlapping intervals in greedy. How do you solve that? What is the maximum overlap that you can have? One thing that comes to mind directly is using the difference array. Okay, but still it will not work here because the size of the the arrival and leaving times is way too big. The memory limit is also 512 MB only, so it will not work. 500 into 10 to the power 6, which is 10 to the power 8, and difference array will require 10 to the power 9 at least. So 4 into 10 to the power 9 bytes, which is megabytes, no, gigabytes. So 4 gigabytes. Not work. Okay. Sorting, no? So Uh, this is all just sorting and searching. I don't like this problem. Greedy problems at all. So yeah, I think. Oh no, maximum subarison. This I can do. Sum of two values I can do. Ooh, I can do this. N in X. LLL. Then I need position. So f I will go from 1 to n plus 1, and I'll check if okay, so first I didn't put, and check if this MP contains this. If yes, then I'll print whatever the MP has. I'll print the position of MP and this, and we'll break it. Otherwise not otherwise I'll just do MP x minus t is equal to I. Okay. Please work, please. Holy shit. Okay, impossible. There's TLE as well. So I'll do this as map, and what do they mean by impossible? No solution, then print impossible. Okay. So I'll set a flag. False. Okay, in we need to break also, na? Done. We are done for today. We are done for today. So we solved two problems and think that is enough, and we'll meet tomorrow. So yeah, take good care of yourself and bye bye.